In this tutorial, we are going to calculate question 12 from our lab manual. This one we are going to do as a two-dimensional equation. We did question 11 as a one-dimensional. The first thing we need to do is write a null hypothesis. Since this is the same experiment as question 11, our null hypothesis is pretty much the same. There is no difference. Remember, null hypothesis is always there is no difference in the effectiveness of the pesticide spray at controlling caterpillar populations. But this time we're looking at red oak and black cherry trees. So the species are different. Now I want to do this as a two-dimensional equation. So I'm going to add two variables. My first variable is going to be tree species. So I'm going to have red oaks and black cherries as my two tree species in variable 1. Now I need a second variable. My second variable is going to be the presence and absence of caterpillars. So I'm going to have caterpillars absent and caterpillars present. Now I'm also going to split this where I have my observed numbers and my expected numbers. I'm making my observed area smaller because I'm just writing down the number I counted, where I'm going to do a little bit of math in my expected totals. In the question, we perform this experiment on 83 young red oak trees and 54 black cherries. And then after a week, we count no caterpillars, so caterpillars absent, on 20 cherries, which is backwards from how they wrote it before, so double check that, and 47 oaks. They do oaks and then cherries and then oaks, which confuses people frequently. This means we have 137 trees total, and 67 of them are missing caterpillars. So we can fill in the rest, where we have 36 trees with caterpillars that are oaks and 34 that are cherries, which comes to 70. So 67 and 70 equals 137. I always like to double check my math. So now we need to calculate our expected values. In a two-dimensional equation, expected equals the row total times the column total divided by the grand total. Now, if you recall, our one-dimensional expected was just our total divided by the number of categories. But in a two-dimensional equation, we have two variables. There are two dimensions. We have trees and caterpillar presence. I like to think of this as length and width. When you are measuring a square or a rectangle, if you want to find the area, you have to multiply the length times the width. So now we have totals in rows and totals in columns. We need to multiply those, length times width. And our grand total is the total we're now dividing everything by. This also means that each number is going to be slightly different because our row and column totals are slightly different. So for this particular box, 83 is our row total, 67 is our column total, and our 137 is our grand total. And it's different for each one. 83 times 70 divided by 137. This one's 54 times 70 divided by 137. And this one is 54 times 67 divided by 137. So they're each slightly different. When I do the math, we get 40.6, 42.4, 26.4, and 27.6. And when we add them up, 40.6 and 42.4 equals 83, 26.4 and 27.6 equals 54, 40.6 and 26.4 equals 67, and 42.4 plus 27.6 equals 70. So that's important. They're sharing those rows and columns, so the totals still add up. So when you round, you have to be cognizant of those rounding numbers. So now we have our observed and expected values. We can put them into our equation. So that sum of means we're adding this together multiple times. Plus. How many times are we adding it together? Well, we have 1, 2, 3, 4 pairs. So 4 times. It doesn't matter what order you put these in as long as you make sure your expected and observed pairs are with each other. Now I said before, I like to calculate these in columns because I find it easier on my calculator. So 47 minus 40.6 equals 6.4 squared. And 6.4 squared is 40.96. And 40.96 divided by 40.6 is 1, but I'm going to keep as many decimals as I can. The more you round, the less accurate your result is, so I try not to round too much. 36 minus 42. Oh, look at this, negative 6.4. Again, these positive negative pairs in our numerators are very common. (20 minus 26.4 is another 6.4, not surprising. And I bet you anything this is also 64. Yep. When we add those all up, we get roughly 5. It's like 5.00 something. So this is our calculated chi-squared. So our calculated chi-squared equals 5. We need to find our critical chi-squared. So our two-dimensional degrees of freedom, so if you remember, our one-dimensional degrees of freedom was the number of categories minus 1, which is very similar to our t-test degrees of freedom of n minus 1. Just instead of a number of numbers, we have a number of categories. But now we're looking at a two-dimensional, so we have length times width. So now we're going to have the number of categories in rows minus 1, so length times our width, the number of categories in columns minus 1. So we have 2 categories in rows and 2 categories in columns. So we have 2 minus 1 times 2 minus 1, which is 1 times 1, which is 1. And if you recall, our alpha is always 0.05. And our degrees of freedom is 1, so our critical chi-squared is 3.841. Now, if our calculated chi-square is greater than this critical cutoff line, then we reject our HO, and there is a difference. If our calculated chi-squared is less than this critical cutoff line, we accept our HO, there is no difference. So our critical chi-squared is 3.841. Now our calculated is greater than our critical. Therefore, we reject HO. Our calculated chi-squared has crossed that critical threshold. This means that there is a difference in the effectiveness of the pesticide spray on red oaks and black cherries at controlling caterpillars on red oaks and black cherry trees. This is an interesting result because we just tested the effectiveness of this spray on sugar maples and poplars, and we found that there was no difference in the effectiveness of the spray on those 2 species of trees. So this pesticide is more effective on some trees than others. We saw a difference between red oaks and black cherries, but we didn't see a difference between sugar maples and poplars.